Hello students. Now I want to discuss with you types of reaction intermediates. So these are classified into 8 categories. So first one, carbocations. Second one is carbanions. How to know this all intermediates. So third one is free radicals. Fourth one, carbene. Next, fifth one is nitrene. Sixth one, ylides. Next, seventh one is sigma complex. Eighth one, benzene. These all are the intermediates. Okay, ma? Types of the intermediates. So in this first one is carbocations. First one is side heading carbocations. Carbocations. So generally these carbocations again classified into 2 categories. So generally these are classified into 2 categories. The first one is classical carbocations. Next, second one is non-classical non-classical carbocations. So these are the two types. First one again, classical carbocations. So classical carbocations. So generally here, what is the statement of the classical carbocations? The carbocations which are stabilized by the delocalization of, so the carbocations which are stabilized by delocalization of pi electrons and alpha carbon hydrogen sigma electrons. Alpha carbon hydrogen sigma electrons. So here sigma electrons means these are the sigma electrons. Alpha, sorry, sigma electrons. This is the alpha carbon hydrogen. These electrons, these bonded electrons are called sigma electrons. So these type of carbocations are called classical carbocations. That means these are stabilized by the which one? Delocalization of pi electrons and sigma electrons. So that examples we will discuss. That means these are majorly depends on these all are depends on the which one. No, I will explain it. Carbocations depends on mesomeric effect and hyperconjugation. Hyperconjugation. That is the meaning. Okay. So these two effects also important. Based on these two effects, now this carbocation stabilization increases. So one example now. Example. CH2 double bond CH CH2 plus CH2 plus. In this given compound, now these carbocation, this one is the carbocation. This is the carbocation. So that carbocation is stabilized by majorly. These electrons are called pi electrons. Okay, these are the pi bonded electrons. If these pi bonded electrons donate to adjacent carbocation, now these carbocation is stabilized. Now we can write this one like this: CH2 double bond converts into now single bond CH. Here single bond converts into double bond. Again, this one also get the positive charge. Now further it is involving in the delocalization. Okay, here positive charge, one single bond, double bond. That means pi bond. So this positive charge separated by only one single bond. In the here also same. This pi bond means pi bonded electrons and carbocation separated by only one single bond. Now these are only involving in the delocalization. Localized, delocalized. So localized means stable. There is no change in that. But delocalized means those are not involving in the resonance conditions or conjugation conditions. Conjugation means alternative positions. Here double bond, pi bonded electrons. Here this positive charge alternatively present. These are involving in the conjugation. So that's why this is the example of a classical carbocation. This one is classical carbocation. Next, another one example. CH2 plus this one. Now the name of this compound is benzyl carbocation. Okay, this one is called benzyl carbocation. Above one is called allyl carbocation. Allyl carbocation. This one is benzyl carbocation. Now this group stability of this carbocation, it depends on the conjugation or delocalization. Which electron again? Pi bonded electrons. So this one involving in the again conjugation process. Delocal. This process is also called a delocalization. So this one also stabilized by the conjugation or delocalization of the pi bonded electron. These electrons are pi bonded electrons. Here alternatively positive charge also present. This is the example of which one? Classical carbocation. Now this benzyl carbocation, another one is allyl carbocation. Here pi bonded electrons only stabilizes the carbocation. Next, another type of example. Now in this case, so generally carbon has here hydrogens, three hydrogens. This one attached to one carbocation. So this kind of carbocation is called ethyl carbocation. This one is ethyl carbocation. So this carbocation is stabilized by which electron here? With respect to this is the one system according to the hyperconjugation. Which effect is influenced here? Hyperconjugation. In the above these two cases, these are the mesomeric effects. Mesomeric effect. Here this one is hyperconjugation. Hyperconjugation means delocalization of alpha carbon hydrogen sigma electrons. Alpha carbon hydrogen sigma electron is with respect to this carbocation. This is the alpha carbon. The alpha carbon has hydrogens 3 here. So this are the sigma electron. This one also sigma. This one also sigma. One carbon hydrogen sigma electron donate to this compound. Now this kind of process is called hyperconjugation. So majorly which one here? Mesomeric effect and hyperconjugation. So this carbocations depends on the mesomeric effect and hyperconjugation. So by using this we can stabilize the given carbocations. That kind of carbocations are called classical carbocations. Okay. Next, another one. So the second one is non-classical. Non-classical, second one. Classical and non-classical carbocations. So in this, majorly the carbocations which are stabilized by delocalization of delocalization of which electrons? Carbon carbon sigma electrons. Carbon carbon sigma electrons. Here majorly that carbon carbon sigma electron, these carbon carbon sigma electrons. So those are called here non-classical carbocations. So one example here we will discuss. Example, this is the one compound in this carbon has positive charge. This is the carbocation. If carbocation, here also one carbon atom is present, here also one carbocation is present. So if you break this bond, if you break this one, this carbon get the positive charge, this one get the negative charge. So this one donate the electrons to this carbocation. Now, which carbon carbon bond here broken? This carbocation adjacent to carbon carbon bond only broken here. So we can write this kind of carbocations like this. Up to here, there is no change. Next. Now, here, this bond is broken here. Here another one is. Here making, here breaking, here making. Both simultaneously taking place here also. So that time we can write the positive charge here developed on this carbon atom. Okay, this carbon. So this kind of carbocation stabilized by the delocalization of a carbon-carbon sigma electron. So this one is called non-classical carbocation. Non-classical carbocation. So generally we will discuss only classical carbocations. So non-classical carbocations we didn't use in the any kind of reactions. Mostly very less cases only. That kind of reactions are called rearrangement reactions. Rearrangement reactions. Only this kind of carbocation stabilized by the sigma electron of carbon carbon, that kind of stabilization we will observe only rearrangement reactions. Okay, that one we'll discuss separately, rearrangement reactions. So these kind of conditions are majorly non-classical. So stability of classical and non-classical, which one is now more stable? That condition also I will give the order of that classical and non-classical. So in these two majorly always classical is more stable than non-classical. Classical is always more stable than non-classical conditions. So this kind of stability order. These classical conditions are stabilized by mesomeric effect or another one is hyperconjugation. But in this case, only rearrangement, carbon-carbon rearrangement. So that's why always classical is more stable than the non-classical conditions. Then what kind of reactions follow this classical? and non-classical conditions in this majorly. So the types of carbocations developed in which kind of reactions, that is also very, very important. So carbocation intermediate, carbocation intermediate, develop in the following reactions. In the following reactions. Okay, we will see that examples. First one, example is first one, electrophilic addition reactions. Electrophilic addition reactions. One reaction. Next, second one, SN1 reaction. Next, another one is E1 reaction. So nucleophilic, unimolecular nucleophilic substitution, and another one, unimolecular elimination reaction. Next, another one, third reaction, Friedel-Crafts alkylation and acylation reactions. Friedel-Crafts alkylation and acylation reactions. In this case also, carbocation is the intermediate. Next, fourth one, Wagner, Mervin rearrangement reaction is. Okay, Wagner Mervin rearrangement reaction. Next, fifth one is Pinacol, Pinacalone. This one also rearrangement reaction. Pinacalone rearrangement reactions. So these all are the examples of the intermediate carbocation developed in reactions. So memorize this one also, very, very important. We will discuss separately rearrangement reactions, all kind of reaction mechanism types of the reactions also. Now, these are the only carbocations intermediates. Next, another one is the carbene ions. Second one, carbene ions. Second intermediate, anions. Carbene ions are the intermediates. So generally, these kind of carbene ions formed in general condition, that is condensation reactions. Condensation reactions. Condensation reactions. This point is important. In that conditions only, carbene ion intermediate is formed. These are also intermediate. Intermediate. Now, examples we'll discuss in this. It is developed in aldol condensation. First one, aldol condensation reaction. Next, benzoin condensation. Next, Perkin condensation reaction. Next, Claisen condensation reaction. And Rifar-Matsky reaction. And another one, very, very important, so many times we discussed also, that is in Grignard. In Grignard reagent, in Grignard reagent, the general formula of Grignard is RMGX. So this one is the intermediate RMGX. So this RMGX may exist. One is RMGCl, RMGBr, RMGI. So these are only exist. In this, R is always the negative part only. R minus. R minus means carbon negative charge. Either methyl, ethyl, or any kind of hydrocarbon get the negative charge. So these three only exist in the nature RMGX conditions, but not the RMGF. So another one is RMGF does not exist. This one is does not exist. Okay, these three only exist. Here also carbon ion is the intermediate. So next, another condition is free radicals. Another intermediate, free radicals. Free radicals. So generally we know that free radicals means this one is odd number of electrons present in a given species. Those are only called free radicals. So these free radicals, intermediates, these intermediates developed in intermediate is developed in all types of free radical free radical substitution reactions. Substitution reactions. So, so that examples, no, free radical, either it is a substitution or addition also. Substitution reactions and free radical addition reactions. So these are the addition reactions and substitution reactions. Very, very important. These are the free radicals only. Next, fourth intermediate, carbenes. Carbenes is the fourth type of intermediate. In this majorly, it exists in the nature two types of carbenes. One is singlet, another one is triplet. Singlet carbene and triplet carbene. In these two singlet and triplet carbenes, so how to identify that whether the given carbene molecule is a singlet or triplet? Okay, so singlet and triplet is depends on the M is equal to 2s plus 1 formula. So it depends on the M equal to 2 into s plus 1. Suppose if substitute here s value equal to plus of or minus of like that only. So s means spin old. S means here spin of electrons. Spin of electrons. Now if you substitute in this M equal to s value equal to 1. S value 1 plus 1. Totally you will get 3. So what is the meaning of here 1? That one also I will explain now. So S equal to 1 means this is the one orbital. In this, two electrons were present. Both are the opposite direction. Both are opposite direction. So if both are opposite direction, one is the condition. Wait one second. Sorry. Like this. If S equal to 1 means here both electrons are present in the same direction. So each electron spin is half only. Half plus half plus half. Totally the sum of these two is equal to 1. If you substitute here 1, total value 2 into 1, 2 plus 1 totally 3. So that 3 represents here triplet. That is triplet. But carbon is called triplet. In the given triplet molecule, so two electrons must same direction only present. If you substitute here S equal to 0, if you substitute S equal to 0, so that time you will get M value, M equal to 2 into 0 plus 1. You will get here only one value, that is a singlet carbon. So again same, if S value equal to 0 means the direction of the electrons opposite direction. One is plus half, another one is minus half. So plus half and minus half both 0, you will get a singlet molecules. So this is the difference between the singlet and triplet carbon atoms. Now, singlet and triplet, which one is a more stable? And the representation of the two molecules also I will explain now. Next, carbene molecules. The representation of carbene is CH2. It has one lone pair. This is the empty orbital. This kind of representation is called carbene intermediate. So in this carbene intermediate, how many empty orbitals? One empty orbital, one lone pair with two hydrogens. Now, singlet and triplet carbons, which one is more stable in this? That one also important. Stability of the singlet and triplet. So now, stability. Triplet carbon is greater than the singlet carbon. So this one also important, the stability of the singlet and triplet carbons. So how we can represent the singlet and triplet carbons? So generally this is the one carbon. It has, this is the empty orbital, one hydrogen bonded with this. This is the another hydrogen. Next, the carbon has another orbital with lone pair only. I am explaining about the lone pair. So that lone pair both present on the same orbital with the opposite spin. This kind of representation is called singlet. This one is singlet carbon. Next, if you take another carbon, that is a triplet condition. Okay, this is the one. Like this, two hydrogen atoms. Now, here electrons were present in the given two conditions. So, here one electron is present, here also one electron. So, same direction of the two electrons in two orbitals. This kind of representation is called triplet. This one is triplet. But why these are the stable conditions means this orbital and this orbital both repel with each other in triplet. But in this case, we already paired, but repulsions internally, repulsions more. In this case, already repulsions more in between the two orbitals. Now in that one electron is, it represents like this. Here also one present electron like this. So repulsions in between them is very high. It is already existing in the nature more stable condition. But in this case, inter-electron repulsions more. Inter-electron repulsions. So due to this reason, due to this reason only, triplet carbon is always more stable than the singlet. This is also very, very important, right? Here already these repelled more. That's why here repulsion is very less. Here in this case, repulsion is very high. Here high, here less. So that's why it is a more stable. Okay, this is the more stable, less repulsions. Here more repulsions. So that is the condition. Now, if you observe in the dichlorocarbene condition, dichlorocarbene. Before case is only carbene. Now another one is the dichlorocarbene. In this dichlorocarbene, it exists like this: Cl2, one lone pair, one orbital. This is the dichlorocarbene. In this dichlorocarbene, so which one is more stable? That condition also we will discuss now. Singlet and triplet, which one is more stable? So now this is the one carbon atom. So this carbon has here one chlorine, here also one chlorine atom. Next, this is the orbital. Now electrons present in this 1, 2. Now if you observe, each chlorine also has 3 lone pair of electrons. Like this, 3 lone pair of electrons. Now this kind of representation is called singlet carbene only, dichlorocarbene. In this singlet dichlorocarbene, spin is opposite direction. Next, if you identify another representation, carbon orbital, one chlorine atom here, another chlorine atom here. Next orbital has like this. Then electrons, here one unpaired electron. Take here or here also one unpaired electron, same only, the two different orbitals. Then each chlorine has here also 3 lone pair of electrons. 3 lone pair of electrons. Now, which one is more stable? That is very, very important. Here, singlet is more stable than triplet. Singlet is more stable than triplet. Very, very important. The above case triplet. Here, singlet is more stable than the triplet carbene, dichlorocarbene. So, what is the reason here? This paired electron interrepulsions at the same time. Here, one chlorine only repel with this. But in this given condition, this chlorine repel with one unpaired electron, another chlorine also repel with this one between the unpaired electrons. So repulsions increases more in triplet compared to singlet dichlorocarbene. So that's why dichlorocarbene is more stable than the triplet dichlorocarbene. So these are the two conditions very, very important. And in these two conditions, my here normal carbon it is, this one is a dichlorocarbene. Okay, it is normal carbon. This one is dichlorocarbene conditions. And one more thing in this, the stability order of the dihalocarbons. Dihalocarbons stability. CF2 is greater than CCl2. It is greater than CBr2 is greater than Ci2. Now this one has one lone pair, empty orbitals, the lone pair, empty, lone pair, empty, empty. So in this case, this is the stability order of the dichlorohalogens. So majorly in the first case, there is no empty d orbitals on the fluorine. The lone pair of electron donate to this one, donate to empty orbital in the carbon. So this kind of representation is called, this one is called back bonding. It is called back bonding. So back bonding, due to the back bonding, here CF2 molecule carbene, difluorocarbene is more stable than the other dihalo